So welcome everyone. Thanks for returning after the very definition-based class that we had last time. As I promised, today we're gonna do way more serious stuff, or way more fun stuff at least. We're actually going to apply our things. So let me start the screen share. Go to the document. Hopefully you can see everything here. If you can't, let me know. And just organize the. Right, cool. So let's remember that this is an RQY course technically that I decided to title as Quantum Information Protocols in QFT. Our goal is still the same. Our goal is to couple local probes to QFT in order to implement the quantum information protocols. All right, now today our main goal is to talk about these local probes. Okay, this is what we're going to spend the day talking about. We're going to talk about these, and these local probes that we are going to have, they will be something that many people call UDW detectors or particle detectors. Oops. I don't know what I did here. All right. Or particle detectors. Now, these particle detectors or UDW detectors, the idea is that we're going to need two things or two ingredients. We're going to need a QFT, a quantum field, and we're going to need a localized quantum system that couples to this quantum field theory. So technically, we need a third ingredient, which is one interaction. And the idea here is that we need to describe this localized quantum system. It's localized in both space and time. We want it to be localized in space time. So you remember that in algebraic quantum field theory, basically everything is formulated in terms of the operators phi of f, where these f are a completely supported function of spacetime. So there's a region of spacetime O where this function f is supported, right? So our idea is to try to sample these phi of f's by using these localized quantum systems, which are these particle detectors. Okay. So let's describe each one of the three ingredients that we need. It's actually quite simple to describe each one of these, especially because we already have the QFT review in course. So the QFT there isn't too much to it. We need a quantum field. We're going to follow the algebraic formulation that we reviewed yesterday. So quantum field in curved spacetimes. So basically, we have this algebra of observables, or this association of algebras of local regions to algebras of observables. We have a spacetime M, we have a metric G, we have our smeared field operators, and we're also going to fix the state, omega, which gives rise to our two-point function, which we discussed a little bit yesterday, and also to all of the propagators that come associated with it, right? So what I'm going to say is this is for a scalar QFT, but we can consider more general QFTs. The only thing is that we're not going to have really too much time to go into details into this in the course today or in the course at all. So I'm just going to leave this as a note. there are some references that I can give later to discuss these things, but so we are going to focus in the phi-FF, but everything that we do basically can be generalized to more general quantum field theories. Okay, that's it. That's the quantum field theory. That's the first ingredient. The second ingredient we need is localized quantum system. There are many descriptions for a localized quantum system that we can employ. But basically, the key thing here is that we need a quantum degree of freedom which is localized. Now, in order to localize it, we need to assign an observer who's basically holding this quantum system, and this observer will be undergoing a time-like trajectory. Okay, so in this description here, it's not only that we need a quantum degree of freedom that's localized, we need it to be localized in a time-like trajectory, which will be fixed and given with the particle detector. So a time-like trajectory z of tau. Okay, and tau here is I'm going to assume that this is the proper time of this trajectory. And of course, with this quantum system, it will be described in a Hilbert space. So let's call this a Hilbert space HD, D for detector. And as any quantum system, the system will have a free time evolution that's described by a free Hamiltonian. A free Hamiltonian, which is HD. Okay, so it's denoted by HD. And I will also make the assumption that this HD has at least some, but ideally all of them, discrete energy levels. So that the Hamiltonian has bound states or has some states with discrete energy levels. Now, the thing that I want to mention here before going to the next point is that this HD here, it prescribes time evolution, right? I mean, the Hamiltonian is the generator of time evolution, and the generation of time evolution when we are handling spacetime, that also implies that you have to specify with respect to which time you're generating time evolution with. So this HD, it promotes time evolution with respect to the proper time. So the idea is that if you are undergoing this trajectory z of tau, you want to describe this as standard quantum mechanics, basically. Okay, you want to describe this as standard quantum mechanics, which is to say basically that you're using your own proper time to just describe the states and the evolution of the states and everything like this. You could change to a different notion of time. We're not going to discuss this here, but it's covariant up to some extent, and we will discuss up to which extent it's not eventually, but definitely not today. The last ingredient that we need is then the interaction of the system with the quantum field. Okay, so the first thing that we need is basically to define the spacetime interaction region. And this will be defined by a function that it's very common to call lambda of x. This lambda is what we call a spacetime smearing function. And pictorially, what's happening is that there's this trajectory z of tau, and the interaction between this quantum system and your field will happen in a region which is basically determined by the support of this lambda of x. So you're assuming that this lambda of x is strongly supported around your trajectory from an initial time to a finite time. You can relax all of these conditions. You can consider more general things, but in general, picture this lambda of x as being kind of like defining this world tube, this finite world tube around your trajectory, and this will be the interaction region between the detector and the quantum field. Then, well, if we're going to couple to the field, we need to couple to a specific field observable. So we need to pick a field observable, which we're going to denote as O of x. So this can be, for instance, the field itself. It can be the field squared, or it can be many other things, okay? So you just have to define which observable it is. In most cases here, we're going to use the field itself. We're not going to consider more general cases, but the principles of the model wouldn't change too much with this. And finally, we need an interaction, sorry, a detector observable before the interaction strength. We need a detector observable, or in general, it's an operator, but in this case, let's focus on observables. We're going to call it mu of tau. The idea is that the detector observable is going to couple to the field observable within the region lambda of x, and then from this, we're going to be able to build our interaction Hamiltonian. So this mu, it basically is an operator, a linear operator in the detector Hilbert space. Okay. And finally, we are going to need an interaction strength, or a coupling strength, or a coupling constant. It's a lambda. Okay. And then if you combine these four things, then you can build your interaction Hamiltonian density. And the idea is that this interaction Hamiltonian density, I'm going to now write it at the level of density because I want to talk about the Hamiltonian is a function of the space-time events in which the coupling happens, right? So it's not an interaction Hamiltonian, it's an interaction Hamiltonian density. And it will simply be the product of each one of the terms that we have defined so far. So this literally is coupling so this is literally coupling the operator mu with the field phi within the region determined by the lambda of x, and the coupling strength of the interaction is the coupling constant lowercase lambda. Now, if you want to compute the interaction Hamiltonian, the Hamiltonian itself, what you need to do is simply to integrate this over a given Cauchy surface with the square root of minus g, which encompasses both the induced metric in the surface and any possible redshift factors. Then you integrate this Hamiltonian density, and you find your operator, which is the interaction Hamiltonian. Okay? And the only thing that I'm gonna briefly mention this here, but we're going to get back to this probably in the last lecture. This tau of x is an extension of the detector's proper time locally around the trajectory. Z of tau. So basically, we need to define this notion of time evolution wherever the support of lambda of the space-time Zimmermann function extends itself. And in order to do this, we basically we need to define a time-like coordinate around our trajectory. And this time-like coordinate will be this tau of x, which basically defines the rest surfaces associated with the observable. Okay. we're going to use the Fermi normal coordinates, Fermi normal time. If you don't know what this is, don't worry, we're going to get back to this later. What matters is that you need to pick a time parameter, which is a time coordinate around the detector's trajectory. Okay. Cool. So this is the model. Basically, once you write this down, this interaction Hamiltonian, and once you consider the quantum field and the localized system and everything, now you have your detector model. Okay. And we're going to be working with these detector models until pretty much the end of the course. Our goal will be to use these to sample the correlations of the field and to well, let's see what we can do with this. Let's see what we can extract from the field using these detectors. There are many things to be said about these detectors, and most of the important things I will mention in the last lecture. But from this lecture here until pretty much the fourth, I will talk about we'll mostly be applying this detector. Yeah, sorry, Daniel, you have a question?
Yeah, Nick. Actually, I do. I'm a little confused if we are still in the localized detector, or this lambda is already enough. I mean, this product is already enough to actually make it a little delocalized. Because I mean, I was thinking that actually that
I don't know what you mean by localized detector, because like this is the only model
a
that I've
spatially
presented so far.
localized detector.
Well, it's
No, yeah, but I mean, so far this lambda, if you take, I mean, if you have the point is when you do this integral, the integral that you wrote below, a little below, yeah. So up to this point, I was actually considering that this is only the support at each sigma tau. The support would be only on the curve of the which you are the time life trajectory. But now, I mean, if you need this extension to make this integral, then it's not really supported. It's not a delta, a spatial delta, right? Or it is?
There are two things. One of them is the quantum degree of freedom. The quantum degree of freedom itself is defined along the curve itself. So the mu of tau, the mu only depends on tau. Like the mu is a degree of freedom which lives like here. You see here. This is where the mu of tau lives. Okay.
Yeah, but if you multiply this lambda x and you need an extension of tau, because I mean, in mu of tau, there is no dependence, no explicit dependence on the other coordinates like x, right? There's no dependence. So I see what you mean. That's usually what I say.
Coordinate system. In a specific coordinate system, there isn't, right? But the idea is that you're saying that mu is the same along these specific slices, which are defined by the specific choice of time coordinates. This tau here is indeed a tau of x, but it is such that it's constant in the specific foliation that you pick.
Yeah, so, but then you're also extending the location of this quantum degree of freedom, right?
In a way, yes. In a way, yes, but at the same time, because it's constant along the surface with respect to the tau, you're not.
Well, but it's not, I mean, but so if you, after you do the calculations, you, not after, but I mean, if you really consider, it's independent for this very specific, which is very specific prescription to do the extension. If it turns out in the end to be completely independent of this, that I think it's okay, but otherwise it's not really localized, right?
Yes, what I'm gonna say is that this is one of the things that we're gonna talk about in the end, okay? Which is like why do you use the Fermi normal time, and like how can you?
Yeah, I agree that it's natural. I agree that it's natural to this, but I mean, in the end, if the degree of freedom, the quantum degree of freedom detector really were localized only in the time-like trajectory, in the end, it shouldn't depend on that. So that's but probably
there is a way of linking like the space dependence in the rest frame that you're using to describe the quantum system with the shape of everything, and we will do this, but again, this will be like later because I don't
Okay.
want to spend too much time on the details and like why and whatever. I want to do some calculations and see what we can do with these first. And then
All right.
after
Thank
we
you.
learn that, then we will discuss all of the why it makes sense. Okay. So for
Okay.
now, for all that matters, you can pretend that this is a toy model and has no connection with reality, although it does. But we're gonna talk about this later. But this is a good point. These are all good points. Thanks for bringing them up. All right. So we're gonna focus then on the okay. Um, this is not very good. My pen stopped working now. I'll try to get it back. If it doesn't work, then I have a plan B and I'll have to connect something else. Let's just hope that it works. Because also I'll have to spend like 2 or 3 minutes. Yeah, there you go. It's back. All right. Cool. So the question that what we want to find out right now is what can we do with this model? And to answer this, we're just going to look at an example. Uh, and this is going to be the example that we're mostly going to stick with. So we're going to consider a qubit. So the Hilbert space is C2. The free Hamiltonian of the qubit is simply going to be going to have this energy gap omega and these raising operators sigma plus sigma minus, right? This basically defines the basis, which is the ground state and the excited state. And the idea here is that the raising operators, they're such that sigma minus kills the ground state, sigma plus maps the ground state into the excited state, and sigma plus is the sigma minus dagger. In a matrix representation, well, there's depends on the ordering of the bases. You can compute these things. We're not going to be using the matrices. It doesn't really matter. But now that we picked the HD and the H, now we in the free Hamiltonian, we need to pick our mu of tau. Our mu of tau, which is the operator that's going to couple to the quantum field, is going to be sigma x of tau. And sigma x of tau is basically sigma x with the natural time of evolution that comes from the free Hamiltonian, right? So this will be like sigma x in the interaction picture using the Hamiltonian above. And then what will happen is that sigma plus will evolve with an e to the I omega t, and sigma minus will evolve with this e to the minus I omega t. And with this, this will define us our interaction Hamiltonian. For now, see, we're leaving the space-time, we're letting the space-time to be general. We're letting the quantum field to be, well, in a general state, general in space-time. The space-time is mere function, the trajectory, everything is general, okay? And most of the calculations we're going to do at the beginning are going to be like this, but then of course we're going to specialize to some particular cases to see what we actually get in some cases where we can get some intuition. But basically, so this is the interaction Hamiltonian we're going to have in this case, right? This is what is usually called the two-level UDW model. This two-level UDW model, it's probably the most used and known particle detector model in the literature, exactly because it's very simple, but also so there are many connections with many other physical systems even, provided that you make suitable choices for your space-time smearing function and its trajectory and quantum field and everything. Again, more about this later. What we want to see at first is what is the time evolution if we start the qubit in a given state, start the field in a given state, what will happen to the qubit? Now, this is basically time-dependent perturbation theory in quantum mechanics. You need to compute the time order exponential of minus I, the integral of the Hamiltonian of tau d tau. And we're only going to be interested in after the interaction has already passed. So for tau large enough so that we are already past the support of lambda where the interaction is non-zero. So we're going to be looking after the interaction is switched off. So this every integral I write will always be from minus infinity to infinity. Now, the interesting thing here is that this time order exponential, so I wrote a t here, should have written a tau just for clarity. If you write the interaction Hamiltonian in terms of the Hamiltonian density, we're going to get this written as an integral dv of hi of x. Remember here, dv is root minus g d4x. So it's the covariant spacetime measure. The only thing I'm going to mention is that this time order, for reasons that, again, we will discuss later, we need to time order this with respect to the time parameter tau. Usually you can pick any parameter. In this case, you can't really, but again, we'll discuss more about this later. What matters is that now we can use the Dyson expansion for this time order exponential, which basically says that if lambda is small enough, right, then we can do this series expansion in the Hamiltonian. That's why we want to have the coupling constant. We assume it to be small enough in many cases, not all of them. But then we get the Dyson series. And the Dyson series, I am writing it in this specific form in which I use a Heaviside theta to do the nested integrals, okay? And the reason that I'm writing the Heaviside theta here is because we're going to be able to use this to relate this with the Feynman propagator and the time parameter dependent functions that we had before. And of course, there will be higher order in lambda terms as well. For now, we'll be interested only in the leading or in the up to second order in the coupling constants. Okay.
Rick.
I'm sorry. Is there a question?
Yeah, actually, it's me again. Sorry. Yeah. Just to be, I know it's just a detail, but just to be sure, but because of the notation, isn't there some missing redshift factor like U0 somewhere in the or either in the definition of the little h I or somewhere else, just to match or in your definition of the hi?
It's here.
Capital Hi.
This root minus g. It is the what you want,
yeah,
which is the gamma factor times the root of g sigma, which is the induced metric. But if you use this notation and with the d tau, which is the Fermi normal coordinate time, then you actually get it to match. And again, we're going to see this in the last lecture.
No, but I'm just substituting your hi in this first equality of the ui.
Yes.
I'm just substituting it.
And then you're going to see that you're going to get a root minus g d3x d tau. Remember that d tau is not the proper time outside of the trajectory. The tau is just a time coordinate outside of it.
Yeah. Okay. Oh, but so basically u0 is 1 then.
U0 is 1 on top of the trajectory because tau is the proper time on top of the trajectory. But outside of it, like but tau is just the time coordinate we're using, and d3x are just the space coordinates that span the surface.
Yeah, but what I'm saying is that if you just substitute there, then there is this square. It will become d3x square root of g d tau and not d4x.
Yes, but what I'm saying is that.
But then you have to translate this d tau into gx0, right?
Tau is just the time coordinates. Okay.
Yeah. So that's the point. Then u0 is just 1.
No.
It has to be 1 everywhere where you integrate. Otherwise, you have to do this conversion of tau and x0. You're saying that x0 is tau, right?
No, I mean yes, but my point is yes, x0 is tau, but tau is not the proper time.
No, that's fine. But okay.
Just then,
proper. If you just have one curve, then there's just one one only in that curve that tau can be interpreted as proper time, right? But just to be sure that then x0 is tau. Okay, that's fine.
Yes, yes. Like I'm using coordinates
Okay.
such that tau is the time coordinate. Yes,
Perfect.
yes.
Okay, perfect.
No, I know. Now I got your question. Yes, I'm using coordinates such that tau is the x0. Yes, but the point is after sorry, after you after you write it like this, after you write it as root minus g d tau d3x in a specific coordinate system, this quantity is covariant because it's just the measure. And now this expression is valid in any coordinate system. That's the logic that I missed, that I skipped there. But the point is, after you write it like this once, this is true in any coordinate system. Just again, what matters here is that we're using the tau to provide the time ordering exponential, because time evolution is with respect to tau. Cool. So now, if we want to compute the final state of the detector, this final state will be given by. So you just apply the unitary from both sides, and you expand it. Then you're gonna find these. I'm forgetting hats everywhere. So you're gonna find a mixed term here on the U1 dagger, and you're gonna find another term here, which is the U2 dagger, and order lambda cubed in principle. But what we're really interested in is what is the final state of the detector, not what's the final. Sorry, not what's the final state of both the field and the detector, which means basically that we need to trace over the field in order to find the final state of the detector. And basically the idea here is whenever you're measuring a quantum field, you don't actually have access to the field. You have access to the measurement apparatus that is localized and coupling to the field. And then, so yeah, this is basically why we're tracing over the field. We're assuming that we only have access to the final state of the detector. And if we do this now, what will happen here is these terms that have only the UI1, they're going to have one field operator here with the rho 0. So basically, they're going to have something which is like a phi of x integrated whatever, but this will be applied, and then you're going to have to in rho phi. Okay. Then when you trace things like this over the field, this will be basically this will be 0 if the rho phi is 0 mean Gaussian state. And we will assume that the state of the field is a 0 mean Gaussian state. So we're assuming that the field is in some sort of vacuum, okay? So in this case, we're going to get rid of the 0th order terms, and then this rho 0 is just going to give the initial state of the detector. We're going to get 0 from the two first order terms here. And what we're actually going to have to compute will be the trace over phi of the UI2 rho 0 plus UI1 rho 0, UI1 dagger plus the rho 0 UI2 dagger. And these are the terms we're going to be interested in. So let's assume that the initial state, so say that the initial state of both the field and the detector is rho 0d, tensor product with a rho omega. Let's call this rho omega. So that omega is the notation that we had from the field, which is basically this representation of the state omega. Okay. Now, what we want to compute are each one of these three terms. Notice that the first and the third, one is the conjugate of the other one, but we can compute this fairly easily. So let's see what I mean by this. Let's compute the first term first. So this is the trace over phi of the UI2 rho 0 This term, if you look at the U2 up there, you just have to apply this U2 to the rho zero, right? So this will be minus the integral dv prime, theta of tau minus tau prime, trace over phi of the product of hi of x, hi of x prime. Now I can replace the Hamiltonian by the expression that we had before, which is basically this expression here, but I'm gonna write this as mu of tau. So I'm just gonna write mu of tau and not the expansion in terms of the other things, the sigma plus and minus. And what's gonna happen here is that we're gonna get the space-time smearing functions. The mu of tau are not affected by the trace over the field. They live in the detector Hilbert space. And then we're gonna have a trace over phi of the phi of x prime, rho omega, and there's a rho zero for the detector that we could have written before. But this quantity here is the Weidmann function of the field. This is just omega of phi of x prime. So if you remember the definition that we went for, oh, sorry, nothing is working. Sorry about that. That was a bug in the thing. Okay. But now if I remember the definitions that we had from before, or even before this, let's just like expand this mu of tau, because why not? If you compute this product, you're gonna find out e to the I omega tau prime sigma plus sigma minus. Because sigma plus with sigma plus is 0, and sigma minus is also 0. So only two terms will survive here. Tau minus tau prime sigma minus sigma plus. Now if we plug this all here, this will be the integral dv prime. You can expand these two terms, and I will write each one of the integrals this time, but not after. But this will be lambda e to the I omega tau, lambda of x prime, e to the minus I omega tau prime. Then we're gonna have the sigma plus, sigma minus acting on the initial state of the detector. Then we will have theta of tau minus tau prime, w of x prime. Nice. So this is the first term which comes from the first expansion of the mu. And the other term is going to be very, very similar, but the sign of the omegas will be flipped. So this is e to the minus I omega tau, lambda of x prime, e to the I omega tau prime. Now we get a sigma minus sigma plus. Apply to rho 0d. We also get a theta of tau minus tau prime, w of x prime. Now, if you remember yesterday, we defined this quantity here as being the w tau. This is w tau of x prime. So basically now the operator part that is in the qubit space, which corresponds to this term here and to this term here, they leave the integral completely. And what we obtain in the end is simply something which is it's going to be minus lambda squared, then w tau, which is this bidistribution, applied to lambda plus lambda minus sigma plus sigma minus acting on the initial state, plus w tau now acting on lambda minus lambda plus sigma minus sigma plus acting on the initial state, where this lambda minus lambda plus, it's basically the lambda with the phase. Okay, so the functions I'm having some time scrolling down. Yeah, there. So the function is lambda plus or minus. So where lambda plus or minus of x is lambda of x e to the plus or minus I omega tau. Remember that tau is a function of x, just this specific coordinate time that we prescribed up there. Okay. Oh, so this is what this term is, but in the end, notice as it has to be, this is just operators acting on a qubit initial state being multiplied here by terms that depend on the correlation function of the field and functions like this, integrated with respect to the spatial mirroring with this, or the spacetimes mirroring with this phase. So basically now we'll have the correlation function of the fields integrating regions acting in our qubit. I'm gonna do the other calculation as well because I think it might be valuable. Actually, how much time have we spent so far? Yeah, I'm not gonna do the second calculation, but I'm gonna recommend you to try to do it this by yourself. So if you compute this here, this is easier because there's no time ordering, but it's harder because you can get confused with the order of the arguments. But and also you're gonna have four terms in this case. But if you compute this, what you're gonna find will be lambda squared, and you're gonna have a contraction of lambda plus and lambda plus, and the row 0 being sandwiched between sigma plus and sigma plus. You're gonna have another term which is the W of lambda minus lambda plus, and the row now being sandwiched between sigma plus and sigma minus. Then you will have lambda plus, lambda minus, and the W being and the row being sandwiched between sigma minus and sigma plus. And finally, the last term will be a W of lambda minus, sigma minus rho 0d, sigma minus. All right. So try to get to this result. It's basically using exactly the same thing that we did there, using the expansion of the muse, factoring out the part that depends on the qubit state and the part that depends on the quantum field, and then you're going to find something like this. And finally, the last term that we will need will be the trace over phi of the row 0. Sorry, is there a question?
Excuse me.
Yes,
There's
please
a
go ahead.
question in the chat. The person asking, are we supposing that the density operator factorizes at all space-time points?
I don't know what you mean by that. So the qubit density operator does not depend on spacetime, right? There's like a matrix pretty much that lives in C2. And the quantum field density operator, it's being traced over here. So it doesn't factorize, it just acts, if you will, in the field operators as the states that we are defined in algebraic quantum field theory. But basically, this row 0d, it's a matrix. For all intents and purposes, this is a matrix that lives in C2, just like the sigma plus and sigma minus. So I guess the answer is yes, that it does factorize for every spacetime point. Nice. Okay, and if you do this other term, this other term, it's possible to note that this is actually the, oh, my bad. But this is the conjugate of the first term that we had computed. Great. Sorry. Yes, this is the conjugate of the first term that we have computed. And then we can just take the conjugate of this term that we had there. Before doing this, just okay, I'm gonna write what it is. The result basically is gonna be swapping the tau by minus tau. I'm gonna discuss this very soon. But yeah, so this is lambda plus lambda minus. Now we're gonna have to take the dagger of this. The dagger of this is swaps the order. So we get this, and the other one we get the W W minus tau of lambda minus lambda plus, which now also just swaps the order of the second one, but the second one is self-adjoint, so sigma minus, sigma plus, okay? So now we could write down the final density operator for a general density operator, okay? We could do that. Yeah, there you go. Just needed that parenthesis. And remember that the W minus tau of x prime, it was defined as being theta of tau prime minus tau times the W of x prime comma x. And then you can easily or you can show basically that if you have the W tau of fg and you want to conjugate this, let's actually do this calculation because why not? So if you have the conjugate of this, you're going to have the theta, which is real. So the conjugation doesn't. Oh, sorry, this is the theta of tau minus tau prime. So you're going to have the theta, which doesn't really get conjugated, but then you're going to have to conjugate the f of x and the g of x prime. And you're going to have the w of x prime. This is the definition of the w tau, right? I think I wrote it. Yeah, there. So now, if you want to compute this, oh yeah, sorry, I have to conjugate. Now, you're going to conjugate each one of them, but the conjugate of the Whiteman function is just the arguments just become switched. So basically, you conjugate the f, conjugate the g, but here you just switch the arguments, right? And once you do this, now you can change variables in everyone here. So send x to x prime and x prime to x. And what you end up getting is the integral dv prime of theta of tau prime minus tau. Let's write the g first, because now it's going to come with the x. So g star of x, f star of x prime, and w of x prime. And then here, this is exactly the definition of w minus tau with a star. So yes, I am missing a star here. Good thing that I decided to check it. W minus tau with a star evaluated at g star f star. Cool. And now if you just apply this from the result that we got up here to the result that we have down here, we're gonna get the same thing. Because if you switch and conjugate the lambda minus lambda plus, you're gonna get the same order of the arguments, right? Cool. So now I'm not gonna write the complete final state, but let's consider a particular case, which is the case of the special case where the density operator rho 0d is actually in the ground state in the beginning. So what if the qubit starts in the ground state, and then we which can also be written as this projector here, sigma minus sigma plus. Now, if we want to compute this and we want to find out that the final state, this rho d here, basically we have to plug in sigma minus sigma plus in each one of the expressions we had before, right? Remember that this is a projector. So in this case, for instance, this is just sigma, this is actually 0 because we have a sigma plus squared. But the other term is going to be a sigma minus sigma plus times sigma minus sigma plus. So this would just be sigma minus sigma plus. This one is 0 because sigma plus squared is 0. And yep. Now if you go up here, same things are going to happen here. So basically this one will be 0. This term will remain. And in this one here, only the term that hits it with the sigma plus from here and sigma minus from there is going to survive. And it's going to flip it to sigma minus sigma plus sigma minus instead of sigma minus sigma plus. So if you take everything into consideration, and if one node works, so I'm just going to restart the share for 1 second. Hopefully it's sharing again. So if you just put everything together, what you're going to find is you're going to have the rho 0 term. Then you're going to have the lambda squared w tau of lambda minus lambda plus on sigma minus sigma plus. Then you're going to have the other term, which is the lambda squared w minus tau star lambda minus lambda plus as well, sigma minus sigma plus. And then we get the last term, the only one that survives from the 1 terms, which is going to be w lambda minus lambda plus sigma minus sigma, sorry, sigma plus sigma minus. So sigma plus sigma minus. Now, you might remember from last time that w tau, so w is actually w tau plus w minus tau star. So this is going to be sigma minus sigma plus 1 minus lambda squared w lambda minus lambda plus w lambda minus lambda plus sigma minus. All right, so this is the final state if you start with the qubit in the ground state. And will different observers agree on what the initial state is? That's a great question. We're going to save it for the last lecture. What I'm going to say is, when I say that the qubit starts in the ground state, it means that someone co-moving with the qubit along the trajectory sees it in the ground state. That's a good question. The other question, sorry, sorry, Daniel, what is this a question? Only assume that the initial state is the tensor product, and since this calculation is only perturbative, what enters in the right-hand side expression is the initial product state where the evolution operator second order acts. We're going to do non-perturbative calculations today as well, and I see. But we're going to do non-perturbative calculations as well, and the qubit term is always going to factor as well. So yeah. All right, cool. But basically, going back to matrices, right? What's happening here is like we have something that looks like this. Because this is the projector in the ground state, which I'm denoting as the first element of the basis, and the other one is the projector in the excited state, which is the second element of the basis. And this L term here is basically the lambda squared W lambda minus lambda plus. Cool. Now, let's two things to be mentioned. One thing is, sorry, I'm not going to write one. I'm just going to say, but the thing is, this is a mixed state. Being a mixed state means that, well, we started in a pure state for the detector and the field. Then they interacted unitarily. So the final state of the detector and the field is definitely still pure. But now we traced over the field and we got the detector, which is in a mixed state. This means that the detector is entangled with the field, right? The field is quantum. The field has quantum degrees of freedom. The detector interacts for a finite time, ends up being entangled with the field, okay? And something else that you can see from this is that basically this L, it has an interpretation, which is that it is the excitation probability. You can see this because basically if you compute the E rho D E, then you get L, right? So it started in the ground state, so probability in the ground was 1, and the rest was all 0. With the interaction with the field, it became 1 minus L and L. And that's what we got in the end. Cool. So this is what happens, but this is really not a concrete example. Everything here is very general. We have a general lambda, general spacetime, general quantum field theory. So you know what? Let's focus on a very specific case just to see what happens. So the example of the example Let's go to Minkowski. Spacetime. We're going to consider a massless field. So the equation of motion is box phi equals 0. The state omega, basically we're going to consider the vacuum state of the field. The trajectory that we're going to pick is going to be a z of t, because it's going to be for every it is going to be the product of chi of t in an f of x. Both of these are going to be Gaussians because I want to actually, you know what? I'm not going to even assume that they're Gaussians for now. The only thing that I'm going to say is that the Weightman function in this case for the w of x prime, it can be written as 1 over 2 pi cubed, the integral d3k divided by 2 absolute value of k e to the minus I omega k t minus t prime in inertial coordinates plus I k dot x minus x prime. Oh. So this is the Weightman function, and now we can actually write down the L. We can write down the L, and we can actually do some manipulations with the L term, which is the excitation probability, and we can see kind of like up to some extent on which parameters it depends. And of course, one note, this is all right. Let's see what we can do then. So the L in this case, it's going to be an integral dt dt prime, because it's in the whole space-time, d3x d3x prime. So we also have this term. Now here I'm going to separate things into, well, the chi of t, e to the I omega t that we had from before. But we also have the f of x. So this would be the, with a minus, this is the lambda minus on the w lambda minus lambda plus. So this term. Now we're going to have the chi of tau prime with the e to the I omega tau prime, or t prime, f of x prime. We're also going to have the Weightman function, which I'm already going to replace by the representation above. So the 1 over 2 pi cubed integral d3k over 2 absolute value of k, e to the minus I omega k t minus t prime plus I k x minus x prime. And now we can factor a bunch of Fourier transforms from this. So if we move the integration over k to outside of every other single integral, you see the integral dt of the chi of t e to the minus I omega t with the e to the minus I omega kt, this is just a Fourier transform of chi evaluated at omega k plus omega. And you can do the same thing with f, basically. So okay. So basically, this whole thing can be recast as, sorry, forget the lambda squared. It's an important term. So this whole thing can be recast as this integral d3k over 2k. And now here, we're going to get two terms, basically. A chi tilde of omega k plus omega squared. And an f tilde of k squared. Where this tilde is basically the Fourier transform. So what we're using here is that the chi tilde of omega is basically the integral dt of chi of t e to the minus I omega t, right? Okay, nice. So now we can see a couple of things. First of all, notice that this thing is always going to be positive, right? So it's going to be larger than or equal to 0 in Minkowski spacetime. Okay. This is interesting because this tells us that if you start with a qubit in the ground state, you let it interact with the vacuum of the quantum field, it might be that your detector ends up in the excited state. Okay, so basically, this only happens in the case where the interaction lasts for a finite time. The idea is that you switching on and off the interaction, you will see virtual particles that will come out of this interaction with the field. All right. Nice. And what's also cool about this is that you can actually solve this thing analytically for a couple of cases. So I'm just going to write down the result in the case where you pick Gaussians here. So if you actually pick a Gaussian switching function, which is e to the minus, not really sure if I want to have this pi. No, I don't want to have this pi. E to the minus t squared divided by 2. There's a very good reason why you might want to have a weird pi there, but let's not get into that. But if you consider this to be a Gaussian, okay, and you consider the smearing to also be a Gaussian that has this form here, the standard deviation of the Gaussian in time is capital T. The standard deviation of the Gaussian in space is sigma. And I'm picking units such that in space it's a density, and the chi doesn't have any units, so that in the limit of capital T going to infinity, chi actually goes to 1. Okay. Now you can do this calculation. It's Gaussian integrals on finite intervals. And if you do it, you're going to find that the excitation probability is given by lambda squared over 4 pi. That multiplies e to the minus omega squared t squared divided by 1 plus sigma squared over t squared, 1 minus root pi omega t over root 1 plus sigma squared over t squared. Earth complementary error function of omega t. Complementary error function, this is 1 minus the error function. Root of 1 plus the sigma squared over t squared. Okay, so you can actually get the excitation probability analytically here in terms of all of the parameters. What you will find is that the general shape of this excitation probability will basically be something like this. This is the shape as omega is here and L is here for finite sigma, finite t. And you can plot this. You can see this from the functions that are involved, which basically is this complementary error function just has like this shape, and then you're just going to have a Gaussian multiplying this, and you have a 1 minus this, so you get the opposite kind of effect. But the idea here is that so first, for omega positive, this means that the ground state is actually the ground state. So it's the state with the lowest energy, which is 0, which is where we started. And the excited state has energy omega. So there is a probability excitation, which goes to 0 as the energy gap goes to infinity. Okay. Now, on the other hand, if we're in this regime, which is omega smaller than 0, what actually this means is that what we were calling the ground state is actually the excited state, because it has energy 0 and the other state has energy minus omega, right? So if you consider negative omega, basically you're talking about the excitation probabilities when you start in the ground state. The point here is that in this case, then you have a probability of decaying, okay? And this probability grows a little bit and also goes to infinity as omega becomes arbitrarily large. The key thing here is that the sigma is the spatial size of the detector, and T is for how long the detector is coupled to the field, right? And of course, this L is also an analytical calculation of the W of lambda minus lambda plus, which you could always compute and things like this. And now these scales, the sigma and the omega and the T, they all play a role into like defining what's actually going to happen with the detector. So, for instance, if you take the limit of sigma going to 0 of this L, you're going to find a little bit simpler expression here, but it's a simpler expression which is oops. It's a simpler expression which is kind of fake, and you should be careful with this. I'll explain what I mean by this. Earth C of omega t. I just realized that I missed the term here. Sorry, there's an extra term here. So e2 omega squared t squared divided by root 1 sigma squared t squared. Sorry about that. This factor is there. But this is basically what you get when you take the limit of sigma going to 0. You can just plug sigma equals 0 up there. But now what happens that there's no like this thing now it doesn't look like you're not going to have this peak decaying to the other side as well. Never mind. Let's just keep this expression here and take another limit before we actually sorry, I didn't say that it's in a finite interval. It's in an infinite interval. Sorry, if I said finite, then that's my bad. But definitely the integrals are all in infinite intervals. Because otherwise, yes, my bad. Maybe I mispronounced it. So yeah, thanks for bringing it up. The point is, from this expression, we can also compute the limit in which people really like to compute. Not really like this, but yeah, the limit here, if you now compute the infinitely long time limit for this perturbative excitation probability, you find 0 if the gap is positive, but you find that this diverges if omega is smaller than 0. And you can see that this diverges because basically this Earth goes to 1, the limit of t going to minus infinity, and this goes to infinity, and there's a minus sign, so this diverges. And basically this means that perturbation theory fails. So you cannot be expanding on lambda squared. On lambda, one of your terms so on your series expansion is lambda squared times infinity, okay? So in order to try to understand what happens in the infinitely long time limit, the excitation probability doesn't really help us. And this is a fairly general phenomenon. This will happen in, I'm going to say, most curved spacetimes with most detector shapes. The excitation probability grows linearly in t, which means that the t going to infinity limit is not really, you can't really talk about this limit for the excitation probability. To remedy that, you can talk about the excitation rate instead. The excitation rate is basically the probability per unit time, something that people call f of omega, and it's the limit of t going to infinity of L divided by lambda squared t. Okay. This lambda squared division is not really necessary, but it's more common to define it with this. But now that we're dividing this by t, now we can actually compute what is the transition per unit time. And the result here is going to be minus omega divided by 2 pi, e to the minus omega squared, sigma squared, theta of minus omega. And there's a leftover factor of root 2 pi, which is basically due to the choice of switching that we had. That's why I mentioned before that like there was you could have the pi in the Gaussian or not, and it's a matter of choice there, so that this root pi shows up or not. But basically, this is the transition per unit time. This transition per unit time, if you plot what it is, so this is a Heaviside theta, right? So this means that this is only non-zero for negative energy gaps. So it's only non-zero if your detector starts in the excited state. So the idea is that this excitation rate looks basically like this, and then it becomes 0. So what this means is that if you start with your detector in the ground state and you take the infinitely long time limit, then your detector will always end up in the ground state. So it's not going to absorb energy from the field. But if you start in the excited state, you need contact every second. And you notice if you take the limit now of sigma going to 0, you lose this exponential function. So that's why you should be careful with the sigma going to 0 limit, because this is the plot that you would get at sigma equals 0, which will tell you that this this transition rate actually grows grows proportional to the energy as you have this excited detector interacting with the field. Okay. Okay, cool. So these are the ideas that we can talk about using this very basic detector model. But there's some other things that we can talk about as well, such as we can talk about about thermality. Okay, and I'll briefly talk about the results of a paper, which is here's the archive number, and I'll probably start giving archive numbers for some references from now on. But I think that there's an interesting result. Basically, this paper says for us to assume that when you have your Whiteman function on the trajectory of your detector, this can be written as a function of tau minus tau prime. So this is what we call assume that the detectors are stationary. And this is a property that is deeply linked with thermalization. Sorry, there's a question in chat. I'm just gonna a somewhat related question. Take chi to be a constant from minus infinity to a certain constant t. I'm forced to interpret the calculations interaction being switched off instead of me measuring the detector at a finite time. This is a viable interpretation. How do I interpret a non-zero detection probability? Okay, so the thing is, one thing is what is the Hamiltonian itself? What is the interaction Hamiltonian? And the other thing is, what is the state of the detector or something like this, right? Now, the way to answer this question is basically like, if you say that your chi of t goes from minus infinity to a finite t, then this means that you're saying that the shape of the interaction Hamiltonian, it starts being constant from asymptotic infinity, and then it stops being constant at a certain time. If you measure your detector, notice that in principle, even if you measure your detector, this interaction Hamiltonian is not going to become 0 because you measured, right? Measuring the detector doesn't make the interaction Hamiltonian 0. So these two things are different because of this, like, mathematically, right? Hopefully this answers the question. And thanks for asking.
But how would you calculate a finite time observation then? Because if the initial state, and we're thinking of the free vacuum in Minkowski, right? Yes. So that I don't if I integrate it at any finite time, I don't expect it to be 0. So I always find this disturbing, right?
So you don't want to okay, I see what you're saying. It's not measuring at a finite time, but finding the state of the detector at a finite time. That's what you're saying.
Sure, yeah. All
right, yeah, yes, fair enough. In that case, yeah, these two would be equivalent. Like if you want to find the initial if you want to find the final state of the detector field at a given time t, you integrate it up to t, and it is true that this will be the same as considering switching functions which go up to t and then stop. Yes. You might run into issues if you consider point-like detectors, but I'd rather not talk about these issues because basically for point like detectors, you might face some divergences if you compute it like this because of the properties of the Whiteman function, but this is due to regularization things, and again, I don't want to go into detail in this. But if you integrate this from minus infinity to t, then you find the final state at t, for sure.
Yeah, and I think my concern is just, is this the detector doing what it was supposed to do? Because if it is detecting something, even in Minkowski vacuum, I start to worry if this is, why should I trust this detector?
You see, think of it as like, what you're doing is that you're placing the detector somewhere where it interacts with the field. When you get a very delicate quantum system and you place it somewhere, there's so much noise that you introduce to the thing, and all of this noise is actually like kind of like being very roughly modeled by the shape of your switching function and how you switch on and off the interaction, and it's not even noise. You're not even actually considering noise. So it's like it's impossible for you to make a very, very precise measurement where you're able to perfectly place your detector there so that it doesn't really click unless you leave it there for a very, very long time, really interacting with the vacuum of the field. And like, it's a think of this as it's impossible to really have a perfect experiment. You're always going to be adding some energy when you perform the experiment. That's the way that I think about it. Hopefully,
okay.
Hopefully it convinces you. No worries. Is there another question? Isn't it odd that in the non-zero sigma, an excited detector with an arbitrarily large energy gap will have arbitrarily small rate of de-excitation? Well, this it's not, because there are two scales that control the coupling of the detector with the field, right? So basically, there's two kinds of modes that your detector is more sensitive to. One is the modes which have size comparable to sigma, so energy comparable to 1 over sigma. And the other one is modes that have the same energy as the energy gap of your detector. These two things matter when you're interacting with the field. So now, if you get these two to be resonant, so like omega equals 1 over sigma or something like this, if you get detectors like this, then they will really want to dump off their excitation to the field. But now, if you get a very small detector with a huge energy gap, now because your detector is kind of like trying to dump a lot of energy in modes of the field that it couples to, which are very small, now it's having a hard time doing this, and that's why the excitation probability decreases for arbitrarily large omega at fixed sigma. So that's the interpretation for that. Sorry, Daniel, do you want to unmute?
Oh, it can be. No, actually, but I would understand, for instance, the 0 sigma limit be having some kind of unphysical behavior, but now it seems that actually it's the finite sigma which has some kind of odd behavior, right?
That's what I
because I mean the fact that you are restricting, the fact that you are actually smearing or spreading your detector over a region of size sigma, it doesn't mean that it cannot be actually more concentrated than that. I agree that it cannot. I mean, it would restrict it from interacting with modes with larger wavelengths, but in principle, it could interact with modes with smaller wavelengths than sigma. That would be no problem. But the problem,
then you're sending the omega to infinity if you go like in this way in the plot. So like the of energy, like the energy of the modes that the detector couples to due to its size is basically restricted by this 1 over sigma, right?
Well, but that interpretation is I mean, doesn't seem to maybe a risk interpretation, but that fails completely in the 0 sigma limit, right? Because according to these, in the 0 sigma limit, this should be different from 0.
No, it's smaller than or equal to. That's the point. And then if you take the sigma to 0, now you can't couple to modes that have. Yeah, but then it can couple to all energies.
If actually, well, yes, it can couple to all. Well, it's a little hard for me to understand, but that's fine. I will think more about it. Okay.
No,
Yeah,
fair
that's
enough, but
what this
basically,
result is showing, but it's
Yeah.
it's kind of odd, right? But
I,
okay.
I don't find it odd, no. It's just the 1 over sigma basically tells you the highest energy of the modes that you can couple to. And if you're here, you have no restriction. The sigma equals 0 case, there's no restriction to how much energy you can actually have for your modes. And in the other case, you have a restriction, and then like if you're trying to dump more energy than that there, now probability of successfully damping the energy decreases exponentially.
So
That's what I was
basically,
saying.
you're saying that. So yeah. So basically, this result is basically showing that it's hard for a given finite size detector to couple with wavelengths which is larger than the size of the detector, right? No, actually, it's the opposite. It's hard for a finite size detector to couple with wavelengths which is smaller than
Yes.
the
Yes.
its
Yep.
size.
Because
it
basically
well,
that's
okay.
the cutoff that it
It's
sees
odd
in the
to
field.
me.
You can think of this as the cutoff, basically, right? But yeah,
Yeah.
fair enough.
Okay.
Okay, cool. So coming back to the theorem. So assume that we have a stationary Whiteman function. So basically the time dependence of this Whiteman function is stationary. That chi of tau is adiabatically switched with a given parameter t. Then oh yeah, and also assume a Markovian regime, which some people will argue that you can't really assume at all times, but or for all circumstances, but as and a Markovian regime. Then let alpha be 1 divided by 1 plus f of minus omega, which is the de-excitation rate, divided by f of omega. Then the t being the parallel state of rho d will be 1 minus alpha. And this is non-perturbative. This is a non-perturbative result. I mean, it uses the Markovian approximation instead of perturbation theory. Okay, so this is non-perturbative. And this is for any choice of initial states.
Sorry, what does Markovian mean in this context?
Markovian means that you are assuming that the final state, like the time evolution, doesn't depend on the previous history of the evolution. That's what it means, like in this context. The Markovian regime, like you can really spend a lot of time talking about it and justifying it, but basically you're saying that whatever happens to the detector from now on does not depend on the whole history of the interpretation, just depends on in which state the detector is right now.
But when is this the case? Because the Hamiltonian was.
That's why I said that it's very hard to study the Markovian regime, and some people argue that actually you cannot assume that this regime really happens very often. There are some assumptions like for very high for high temperatures or things like this, you can definitely use this sort of approximation in this case, but it's very hard to really quantify when you can or when you cannot use the Markov approximation. Sorry, I just stopped the screen sharing because again the computer is kind of going nuts here. Let me try to do it again. Yeah, I'll have to just restart things. Sorry about that. Let me restart OneNote. Right. So, and now I should be able to screen share again. Sorry about that. So, there we go. So then you find that, and I'm just gonna say that this one is alpha alpha. Okay, this is an e to the minus. Well, I'm not gonna say anything because it depends. This is true for general alpha, but an application of this. An application of this is when you consider the detector to be in Minkowski spacetime, moving along a uniformly accelerated trajectory. So 1 over a cosh Lynch, 1 over a cosh theta. The rest here doesn't matter. I'm going to just set it to 0. So in Minkowski. Now, if you do this, you actually find that the limit as the adiabatic parameter for the interaction goes to infinity, gives you 1 divided by 1 plus e to the minus 2 pi over a omega, 1 e to the minus 2 pi for a omega, which is of course e to the minus beta h divided by the trace of e to the minus beta h, with beta equals 2 pi over a. And hopefully this rings a bell for you. This is a thermostat. This is thermostat with temperature a over 2 pi, right? Well, with the Boltzmann constant, if you will. This is this one way of seeing the under effect. So if you put a uniformly accelerated detector interacting with the quantum field for adiabatically switched with acceleration a in the vacuum of Minkowski spacetime. So the vacuum, let me write this here. Doesn't really have to be the vacuum, but yeah, okay. In the vacuum, then you will find that your detector ends in a thermostat, okay? Which is the under effect, which probably you have talked about in the QFT and curved spacetime course. Now, comments. The comments that will not address but recognize a couple of the questions that were asked here. One, these detector models they seem like complete abstractions. But they do correspond, or in some regimes they do correspond to physical systems. In many, many cases, but they do. Two, there are important comments that I have not commented, but they're important comments about causality, covariance, and relativity that have not been mentioned. 3. These particle detectors or detector models that we discussed can be generalized a lot, can be generalized to detect neutrinos, gravity, electromagnetism, pretty much any quantum field. And 4, the choice of time function tau of x has to be physically justified. I can just pick the parameter at my own will. So that's what I have to say about it. I have to say that these will be addressed on lecture 5. We're not going to talk about any of these now. These are all things that these are all super fair questions that I do not want to get into right now. So I won't get into right now. I will get into all of them together in lecture 5 when we're going to talk about how to obtain these particle detector models from actual like atoms interacting with the electromagnetic field and things like this. So how much time can I do this in 15 minutes? I'll sketch this in 15 minutes. There's a special case that I'd like to mention just before we end today, which is particularly different from the case that we worked on or worked with today using perturbation theory. There are actually 2 special cases, but they're basically the same. So I'm just going to focus on one, which is the case where omega equals 0. Okay. So when omega equals 0, what happens is that our interaction Hamiltonian or interaction Hamiltonian density will become lambda times sigma x times lambda of x, phi of x. So now this does not vary in time. If this doesn't vary in time, now there is a way of computing the final state of the detector analytically, with no expansion, no whatever, non-perturbatively. Okay, so you don't need to assume the lambda is small or anything like this. The way to do this is to use the Magnus expansion. So what is the Magnus expansion? The Magnus expansion states that U of t equals the time order, if U of t equals the time order exponential from minus infinity to t of, well, dt prime of an operator, let's call it, what, b? A. A of t prime, then this U of t, it can actually be written as the exponential of an infinite sum of operators bn of t, where the b1 of t is going to be the integral from minus infinity to t dt prime a of t prime. The b2 of t will be an integral from minus infinity to t dt1 from minus infinity to t1 dt2 of the commutator of a of t1 and A of T2. The B3 of T will be integral, but then we're going to have commutator of A of T1, commutator of A of T2, commutator of A of T3, plus other triple commutators. So all of this will be triple commutators. I don't know who has seen the Magnus expansion before. It's not very common to see it in many places, but it's a super, super useful tool for us, okay? Especially in this case, because these triple commutators are all going to vanish when you consider gapless detectors, okay? So for omega equals 0 detectors, so gapless detectors, now what we have, the u that we want to compute is basically the time order exponential of the integral from minus infinity to infinity dt of our hi or d tau. Let's call it tau. Hi of tau. So the Magnus expansion tells us that this u will be the exponential of a sum from n equals 1 to infinity of operators theta n. I don't know why I decided to call them theta here, but that's going to be theta, where theta 1 is going to be minus I the integral dv of the Hamiltonian of x. But this is just going to be minus I lambda. Now mu leaves the integral even because mu doesn't depend on tau, mu doesn't depend on x. And we only get the phi lambda, where lambda is the spacetime's mirroring function. So it's a pretty simple operator. This is literally just this mirrored field operator. Theta 2 is going to be minus the, oh yeah, sorry, there's a factor of 1/2 that I forgot to write here. Factor of 1/2 here, and here there's a 1/6. That's how it works. So this will be minus 1/2 the integral dv prime, and in order to implement the nested things, I'm going to use a theta of tau minus tau prime. And then we have the commutator of hi of x and hi of x prime. Cool. So this commutator here, look, mu commutes with itself now. It wouldn't commute with itself at different times if it was varying on time. But now mu leaves this commutator. Let's remember the hi. This is the mu, right? So mu leaves the commutator. The lambdas don't commute. They're just functions. So of course they commute with everything. So this thing here just becomes minus 1/2 the integral dv. Well, actually I can dv prime of the theta of tau minus tau prime, the commutator of the field. That's the only thing that doesn't commute here. Here we get a mu squared, and there's the lambda squared. Oh, sorry, my bad. Forgot the space-time mirroring function. So lambda of x prime, the mu squared, which to be honest is just identity because our mu is just a sigma x. And the other term that we find here is a lambda squared, which is the interaction at the lambda. So basically, this thing here is the retarded minus advanced Green's function with an I in front of it. But you remember that if x prime is here, gr of x prime only has support here, and ga of x prime only has support here, which means that the ga is going to die. So in the end, this thing here becomes minus lambda squared divided by 2. The retarded Green's function evaluated at lambda, mu squared, which is identity, so shouldn't even write it. And that's it. It's done. And there's an I there that I missed. Okay. So this is just a global phase. And most importantly, this thing here is proportional to the identity. So the second commutator is proportional to the identity, which means that theta 3 is going to be equal to 0 because it depends on the commutator of something with the second commutator. So a triple commutator is always going to be 0. And the same is true for every theta n for n larger than or equal to 2. Cool. So in this case, basically, the UI that you're going to find, the unitary time evolution operator, it's simply e to the minus I lambda mu phi lambda, and then we get another term here, which is just a global phase. And this term doesn't matter. It's a global phase and a unitary. It doesn't affect the dynamics at all. Okay, so this term here doesn't really matter. And now using this U, together with the fact that, so I'm just gonna write here the final result because it's already getting late. Don't want to, yeah. So using that omega of e to the minus I phi f is e to the minus 1/2 w of ff. What we find here, we find so the final result, the final state of the detector is given by, so rho d, whatever it used to be the initial state. Once you trace over everything, you can write this as being e to the minus xi cosh of xi rho d 0 plus sinh of xi mu rho d 0 mu. And xi is lambda squared w of lambda. If you this show this not parse, you just have to the here now you that rho d is the trace over phi of u rho d 0 rho omega u dagger. U dagger. And then you can play a little bit with the rules for the commutation relations, whatever. We will talk more about gapless detector when we consider two detectors. And a final comment is it's that if your lambda is a delta of tau minus t0 times an f of x, this implies that your detector is effectively gapless. Because then there's no time evolution. This is basically an interaction that only happens in a spatial slice. So everything that we did for the gapless case is also true for the delta coupled case. You just have to replace the f's, the lambdas that we were using there by f's that have the direct delta, whatever. The point is this results also applies to this case. Cool. So yeah, I think that this is what I wanted to cover for today. So this is one detector. Next lecture is going to be two detectors, and we're finally going to be able to talk about entanglement and exchanging information between the two. Next lecture will be tomorrow, same time that the lecture of today started, whatever you are in the globe. If there are any other questions or if anyone would like to discuss anything, feel free to say something else. Thanks for your attention. And I'll stop the sharing. So any final comments? All right, cool. So I'll see you next time then. Thanks for your attention. Let me stop the